Hi guys, today we're going to take and put conservation of momentum and conservation of energy together. This is my third take on these video notes, so let's hope I don't screw it up this time. We're going to first dive into each of the three collisions and going over what I hope you came up with during your lab. So for this first one, the elastic collision, I mean the perfectly 100% elastic collision, momentum and kinetic energy are going to be conserved for this one. Now, let's be honest, this is not a realistic situation. There are no perfectly elastic collisions. However, we're going to say billiard balls or pool table balls. That's probably the closest we're going to get. That leads us to, okay, if something's not perfectly elastic, then most of our world is somewhat inelastic. Even if things bounce off of each other, we're going to look at somewhat inelastic. In this situation, kinetic energy is not conserved. And as I'm going through these notes, if you need to pause to write down everything, just pause the video. So momentum in the system is constant and conserved, but kinetic energy is not conserved. So this means the colliding objects don't stick together, but there's internal energy and internal energy increases during this collision. This can be through heat, sound, light. Examples of this would be a volleyball bouncing off of your arms. If you went to hit a volleyball, you'd feel that heat. Or if you're jumping on a trampoline. So the third type of collision we have, we're not really going to look at explosions. Yes, explosions exist, but when we come down to this, we're not going to look at explosions. The third type is the completely inelastic. These are when the objects stick together. This is what we've been talking about for inelastic, completely inelastic. Typically, a large fraction of the kinetic energy is converted into thermal energy. That means Ke is not conserved. These are really hard to write. Here we go. Examples of this would be if you catch a football, any sort of catching going on. If a car crashes and they stick together, kind of like when we were originally going over these types of examples. So what I want you to take away in this first one, the only place that energy is conserved is elastic, and that means completely elastic. In these two, energy initial is not equal to energy final. Now, this is a very, very popular question. I haven't written the test yet, but I'm pretty certain. I know myself, and I'm going to ask a question along the lines of like, what type of collision is this? And you're going to have to check explosion, elastic, inelastic, and you will have to explain why. If you are saying it's an elastic collision, you need to prove that kinetic energy is conserved. You have to do it. There will be points on the thing if it's that. If you're saying it's inelastic, you need to prove that energy is not conserved. Because if we look at this, momentum is always conserved. So saying momentum is conserved isn't really fair because momentum is always going to be conserved in a collision. However, energy is not. So let's dive into this and see how we can put this this idea of energy and momentum both being conserved into play. Our first question says, a 4-kilogram ball is moving east at a speed of 5 meters per second, and it strikes a 2-kilogram ball at rest. So if we're going to draw the picture of that, I always like to start by drawing a picture. I've got a 4-kilogram ball. If I can even write a 4, let's make it a bigger ball. That might help. A 4-kilogram ball, and it's moving to the east at 5 meters per second. And then we've got a 2-kilogram ball sitting here, just doing its own thing. Its velocity is 0. So what we're going to do, we're going to start this problem, and we're going to start by looking at conservation of momentum. Conservation of momentum is the idea that momentum initial is equal to momentum final, which would be m1 v1 plus m2 v2 is equal to m1 v1 plus M2V2. M1V1, yeah. We can also pair this with the idea of conservation. Actually, let's just finish working this out and plug in what we know. We know we've got a mass of 4, a velocity of 5, plus a mass of 2 times a velocity of 0 is equal to 4 times VI, or V1, plus 2 times V2. Now, we don't know what the final velocities are. That's what we're looking for. We're looking for the velocities of the two balls, assuming a perfectly elastic collision. So this is all I can do. I don't know those final ones. I can simplify this down and clean it up and get 20 equals 4 VI plus 2, V1 plus 2 V2. That's about as far as we can go. We know that they were looking for the final velocities. Now we're going to pair in conservation of energy with this. Now there is a special conservation of energy equation. I'm going to post a video to show the derivation of this equation. This is one you're allowed to just state. This is one of those few equations that you probably want to memorize, but it is V1I plus V1F is equal to V2I plus V2F. This is something you can totally memorize. It is a weird version of the conservation of energy equation. Super weird version. In the derivation mass, they get mass to cancel out, and you're just able to look at the velocity ratios. So we're going to use this equation. If you're wanting to know where it comes from, I will have the video posted. You do not have to watch the video. So V1I was 5 plus V1F. V2I was 0 plus V2F. So when we're done, we get this equation of 5 plus V1F equals V2F. And I don't have F's on the other side, but that's okay. So now that we've got this, we can take this equation, this V2F, and plug it in over here for V2, which is what we're going to do. So we're going to get 20 equals 4V1 plus 2, and I'm going to plug in that whole thing over there, 5 plus V1, and I'm going to drop the F's here. So we're going to clean this up. 20 equals 4V1 plus 10 plus 2V1. I'm going to subtract my 10 to the other side. So 10 equals 6V1. And we're going to solve for V1. So our velocity one, I'm going to bring the F back, final, is equal to 1.67 meters per second. So that's one of our answers here. It's asked for, this is one of them. Once you get one of your velocities, you can just plug it into the other equation to get your other velocity. So I'm going to go over here and plug that in. And I'm going to say 5 plus 1.67 is equal to 6.67 meters per second. And that's our velocity too. I'll box that in there. Now we could go and check these. We can go back, and if we really wanted to, I can go back and plug this in up here, plug this in up here, and our total momentum should equal out to 20. Well, let's just check that just for fun, just to make sure we did our physics right. So 20 is equal to 4 times 1.67 plus 2 times 6.67. Grab my calculator so we can check this. 4 times 1.67, and it might be slightly off because I did round, equals 6.68 plus 2 times 6.67, 13.34. Both of those values added together give me 20.02. I'm going to say that's good just because that's close enough. I rounded, so of course we're going to be slightly over. So this is one way we can use conservation of energy. It's just a way for me to eliminate more variables for you and make your life more difficult. But keep in mind, this equation is a lifesaver. If you don't use this equation and you use the full conservation of energy equation, you have to do not trig, but you have to do some foiling. You have to do quadratic equation. You're going to get two answers and have to figure out which one works better. It's not fun at all. So just memorize this equation. Memorize this. Not on your equation sheet, but memorize it. If best way to memorize it is to watch that supplemental video I'm going to post. All right, second problem. We're going to look, this one's called a ballistic pendulum. That's what this problem's called. So a 70-gram bullet is moving east at 400 meters per second, and it strikes a 1.2 kilogram block on the right and becomes embedded in it. And we want to know how high will the system rise above its original point. So I'm going to draw a picture to help us wrap our heads around this problem. So again, not an artist, but we've got a bullet and we've got a block, and the block is just hanging there. We know that our block, this is situation I. Our block is just sitting there, and our bullet is moving at 400 meters per second. We know in our final state, so actually I'm going to call this initial state, not state one. We know in our final state, our box has moved up, and there is now a bullet embedded. We know there's going to be a change in height of h. And that's what we want to know. What is that change in height? This is our final. Super, super, super popular type of question. So we're going to start by looking at our initial and then our final and see what we can figure out. We know we can use, we're going to start with using conservation of momentum, then we're going to use the conservation of energy. Because a big red flag for me to know that I need to use energy, it's asking me how high. It's asking me H. The only thing here that I'm going to have H involved with is our energy. And I'm going to write this down just so you guys have this. It's a ballistic pendulum. We actually have one of these that I can get out and show you. If you take AP Physics C, you probably will look at it a little more in depth. So some things we need to know before we dive in. This is a, so during the collision, when it's going, the bullet is going into here, this is an inelastic collision. So we know that momentum is going to be conserved, but energy is not going to be conserved. That's during our collision. However, after it gets embedded and the thing starts to move up, then we're going to have energy conserved. So for part 2, energy initial is going to be equal to energy final as the block bullet system moves from the lowest height to the highest height. So for our initial state, I'm going to start with that one. And I'm going to start here. For our initial, or for point, I guess that's why I labeled it part. Oh. Okay, I'm going to also go back. I'm changing something, sorry. I'm changing my mind. I reserve all rights to change my mind. We're going to call this part 1, and then we're going to call this part 2, just because there are 2 parts to this problem. So for part 1, we know energy and, we know momentum's conserved, energy's not. So I'm going to do a momentum problem here. We know that momentum initial is equal to momentum final. So I'm going to say M1 V1. I'm going to skip M2 because the block was just hanging, is equal to M1 plus M2 times VF. That's because they become one object. We know that 70 grams, 70 divided by 1,000 is 0.07. So 0.07 times our 400, because we want to make sure we're using kilograms, is equal to our 0.07 plus 1.2 times VF. So this is going to be 28. So we have 28 kilogram meter per second is equal to 1.27 VF. So we're going to get a velocity final of 22.05 meters per second. So that's how fast the block and bullet combination system is moving as we switch from I to I2. I mean, from 1 to 2. I don't know why the Roman numerals are throwing me off. So we can get this velocity. Next, we're going to go into our second state. I labeled this initial again. It should have been labeled number 1. My bad. State number 2. Maybe I'll be consistent in a couple of years. For state number 2, now that the block and bullet are embedded together, we're going to look at what happens as it goes from the 0 height to a height that we're actually solving for. So when I'm looking for a change in height, we know we can use conservation of energy. So energy initial is equal to energy final. This gives me K is equal to gravitational energy because we were moving and then we had height. And I'm going to say that 1/2 mv squared is equal to mgh. Now that we're past the collision, our mass of our system isn't going to change anymore. So the bullet's not going to exit the block as it goes up. It's just going to stay in the block. So the mass can cancel, which gives me 1/2 22.05 squared is equal to 9.8 times h. Again, you're welcome to use 10. No big deal. You can do that. I just don't use it. It's no big deal. So when we do this, we get 243.04 on this side is equal to 9.8 h, which gives us a height of 24.8 meters. All right, let's continue on. I've got a couple more examples. I'm honestly not really sure how long into the video we are. If you feel good about these at any point, this is really what we're going to keep doing is practicing this. So the next one, I've got a little bit of trig into it, but we're just going to keep adding layers. So if you're at any point, you're like, I have got it, I'm good, then you're good. You don't need to worry about this. So our next one, blocks A and B are pressed together with a spring between them. When the blocks are released from rest, the spring pushes the blocks apart. So the 0.75 kilogram block A moves up the incline to the left, and the 0.25 kilogram block moves to the right at a velocity of 3 meters per second. We want to assume friction is negligible, and we want to know the distance A slides up the ramp. So we're going to look for D here. This is our goal right here. So we want to start by defining our systems. We know we've got kind of a couple things going on. When I'm looking at this right away, I know I'm going to have like my first state that I'm going to look at, and I'm going to have a second state that I'm going to look at up here. I really care like what's happening before they're compressed and like as they're being compressed, what's happening there, because I need to get that velocity. So I know I'm going to get that velocity, and then I care how high up the ramp it's going to go. So let's start with 1, and we're going to look at that explosion there. So with the explosion, we know that momentum initial is going to be equal to momentum final. But since it's an explosion and nothing's moving at the beginning, our momentum initial is 0. So then we're going to get m1v1 plus m2v2, the momentum of each object. So 0 is going to be equal to 0.75 times our velocity, which is what we're solving for, plus 0.25 times 3, because we were told that that block of B is going to move 3 meters per second. We were told that right here, 3 meters per second. So with this, I'm going to solve for what my velocity final for the block A is going to be, which is -1 meters per second, which checks out with what we know. Looking at this picture, if block A goes this way at 3, we know that, I mean, block B goes to the right at 3. We know block A, when the spring lets go, it's going to have to go in the opposite direction. And we now know that that's at -1. Let's throw some units on there and be a good physics teacher. So once we have that velocity, now we can find the height we go up the ramp by using conservation of energy and essentially then solve for D. So let's continue. Part 2, we know that we're now going to go up a ramp. So we know, kind of like we did the last one, kinetic energy is going to be equal to gravitational energy. So we can say 1/2 mv squared is equal to mgh. And we're going to cancel out mass because the mass of block A is not going to change. This gives me 1/2 times my -1 I just got squared is equal to 9.8 times h, which gives me 0.5 is equal to 9.8 h. And our height up the ramp is going to be 0.5 meters. That's not the D I was looking for, though. This value that we just solved for was this height. Now, if we know the length of one side and we know the angle of our triangle, we can easily, because you guys are all super smart math people, and solve for the side of our triangle, 0.05, and we've got 30 degrees. Since it's the opposite and we want the hypotenuse, which is going to be equal to T, we're going to say that sine of 30 is equal to our opposite, 0.05, over our hypotenuse, which I'm going to call D. Remember, you can flip-flop these two values. So we get a distance of 0.05 divided by sine of 30, which gives us a distance of 0.1 meters. I like what the ability of momentum gives us, the ability to do more stuff. I'm really excited. I like this problem. All right. And I've got one last problem I'm going to go over with the notes. It's probably one of my favorite problems. It's a realistic Spider-Man problem. So it says Spider-Man is climbing up a building on one side of a 10-meter wide street when he spots Mary Jane, MJ, 10 meters below, standing on a platform on the other side of the street. The platform is about to explode. Do you guys see the bomb down there? There's a bomb. The platform's about to explode. So Spider-Man swings down using his web and grabs Mary Jane, hoping to swing her up to an open terrace 5 meters above the platform on the same building where they would be safe. I want to know, will they make it? So looking at this, we've got 3 different setups. It's already labeled in our picture. We've got the part where Spider-Man's going to swing down to her. We've got the part where Spider-Man's going to catch her, which is our collision. It's an inelastic because 2 bodies are becoming one. And then we've got the part where he's going to go back up. So when I'm thinking about this, as I'm approaching this problem, I'm thinking we've got gravitational energy to kinetic energy. We've got a collision. So I'm just going to draw this for a collision. And then we're going to have new kinetic energy up to gravitational energy. I know that my energy is not going to be conserved in my collision, but energy can be conserved when we're not having a collision. So we're going to have 3 setups here. Part 1. In part 1, we're going to have gravitational energy turn into kinetic energy. So that's what we're going to write. We're going to say gravitational is equal to our kinetic energy, and we're going to plug that in. mgh equals 1/2 mv squared. The mass of Spider-Man is not changing during this time. So then I'm going to rearrange this because we don't actually have very many numbers. Technically we can calculate this. But you know what? Let's get a little crazy. Let's just do this all in variables because we can. So when we solve for this, I'm going to call this VI. When we solve for this VI, we're going to get the square root of 2GH because algebra. I'm going to call this H1 as well because that's our height initial. For number 2, this is our momentum part. This is where Spider-Man is catching MJ. So momentum initial is equal to momentum final. We're going to call this mass of Spider-Man plus VI times VI is going to be equal to the mass of Spider-Man plus the mass of MJ times, and we're going to call this their final velocity, or let's call it V2. So when we solve for this, I think it says that MJ and Spider-Man, if you look up here at the image, MJ and Spider-Man have the same mass, which makes our life way easier. Oh, and since they're not giving me my mass, I have to do it this way. Guys, we have to do the problem this way. We can't get away with not using it. So we're going to be able to rewrite this to say MVI equals 2MV2. So let's divide the 2M across. Because then the mass doesn't matter. So we know that 1/2 of VI is equal to V2. So we're getting there. We're getting some equations. We're getting some work in. Now our third one, I need to make this grow a little smaller. This guy was creeped out a little bit. Shrink it down. There we go. So this third part is when Spider-Man and MJ now swing up. And if we look at our picture from the beginning, we've got kinetic energy at the beginning and gravitational energy at the top. We're taking all of this. This whole semester is spiraling in review. So kinetic energy is going to be equal to gravitational. So 1/2 mv squared equals mgh. This is technically the mass of Mary Jane and Spider-Man, but since mass doesn't matter in energy and it cancels out, we don't really have to worry about this. So this is 1/2 v2 squared, because this is the velocity of them after the collision, is going to be equal to g, and I'm going to say h2. Now this h2 is actually what we're solving for, I believe. You know what we're solving for? Yeah, we're going to solve for this H2 because we need to know if he's going to make it up to the platform. So I'm going to highlight this just so we don't forget that that's like the end goal. That's the end game. You get my Marvel jokes, you get them. If you don't, that's okay. And we're going to get G by itself. So when I'm going to divide that to the other side, we're going to get V2 squared over 2G is equal to H2. So now what I want to do is I'm going to take and put all of these equations together. Because if I line up my 3 equations we just came up with, we get, for number 1, we have I'm going to call it V1, VI doesn't really matter, is equal to the square root of 2G H1. In our second one, we got 1/2 V1 is equal to V2. And on our third equation, we got H2, which is like endgame, equal to V2 squared over 2G. So we're going to plug this into this. Then we're going to plug this into this. So we're going to get a little crazy. This is a brutal problem. If you can do this, if you're following with me, you've got this. So 1/2 of the square root of 2GH1 or HI, doesn't matter, is equal to V2. Then we're going to plug that in. So we're going to get H2 is equal to 1/2 square root of 2GH1 squared over 2G. Now we got to do a little bit of algebra finagling. We got to put that squared into places, which gives us, yeah, I'm okay with this. I'm trying to follow my algebra and we're checking that stuff. We're going to start by squaring everything inside of this. This gives me 1/4 2gh1 over 2g. I'm going to bring that 1/4 to the bottom. And we're going to cancel out some. Okay, we got to clean this up a little bit. Let's cancel out the g. G doesn't matter. Woo, that's great. Let's see, the 2's don't matter. We can cancel those out. So really what we get when this is all said and done, we're going to get H2 is going to be 1/4 of H1. So we go back up to our picture. How high did Spider-Man start? Spider-Man was 10 meters off the ground when he started. So we're going to plug that in. 1/4 of 10, which means Spider-Man makes it a height of 2.5 meters. So the real question is, did they make it up to the 5-meter platform? Nope. Here we're even going to get a little more brutal. That's not what I'm looking for. Let's see. I don't think I can find it. I'm going to find it. I'm dedicated. It's definitely not worth all the time it's taking me to search to find this emoji. I'm trying to find the explosion emoji, but I don't use my iPad enough to know where it's at. Oh, well. Lost the point. You guys knew what I was going for. There, we'll just go like that. This is kind of a dark emoji to put. Boom. Boom. There we go. That's definitely not a big emoji either. Oh, well. There we go. Spider-Man did not make it. Unfortunately. Boom. There goes Spider-Man. No, he did not make it. What I would like to point out, I'm going to post this PDF on Schoology so you can see my notes and you can see that as I go through it and see my steps. I'm also going to post this video. Obviously, there are some more ballistic pendulum problems here, and there's some more problems. I will make sure that I'll post the blank version and a filled out version so you can use these as practice on your own. I would encourage you to, I'm not going to post the video of me going over them, but I would encourage you to try these on your own before you go and look at the answer key. I will be back on Friday, so if you have any questions, feel free to come by during ACT Lab and ask away. I know this is challenging, but really the key I want you to get away is we can use momentum and energy interchangeably. We need to know that energy is conserved only in a fully elastic situation. Every other time it's not conserved, but that doesn't mean we can't use it to help us solve problems. All right, guys. I know this is a long video, and thank you for bearing with it. Have a great day, because I don't know what time you're watching this. Bye.